Hello and welcome to Module 8, Six Sigma Approach. Here we will talk about process capability. First of all, let's start off with a definition of process capability. In this case here, we'll call it the ability of a process to deliver a defect-free output, a service, product, or information. This is based on the understanding of the critical whys that we discussed earlier. And this is basically against measuring the performance versus your customer requirements. When you look at process capability, there's certain terms that are key to understand. The first is unit. One count of the process output is considered a unit. This could be one product, one payment, one shipment, one hamburger, etc. Defect. We talked about definitions of defect earlier, but in this case here, we'll call it an item or service that does not meet a specification or requirement. In this, for example, a hamburger could be cold, it could be missing a pickle, undercooked, or etc. A defect opportunity is a chance for the defect to occur with an individual unit. The hamburger could have the wrong serving temperature, condiments, etc. And then defective. Not exactly the same as a defect. This is an item or service or one or more defects that is unacceptable to use. So if any one of those above defects occurred, the hamburger would be failing to meet expectations. A defective item could have one or could have 5 different problems with it or process defects. So defect versus defective is something that many people struggle to understand and comprehend from a Six Sigma perspective. A defective measures the ultimate output of the process and whether or not that product is useful. In the case down there of a check, the defective check would be that the check could not be processed versus a non-defective check would be the check can be processed as is. Now the defects could be all throughout in there could have an incorrect payer, could have incorrect date, amount, could have a poor signature, incorrect routing number. Any one of those defects would have the opportunity to make the entire check defective. Looking at process capability, there are numerous measures that are used today. These ones here that we'll talk about are some of the more common ones, but the reality is many of them exist and that we can only get into so many within the confines of this course. First, we'll talk about capability indices, CP and CPK. We'll talk about first time yield, rolled throughput yield, and then there are other ones that we will not cover, which include sigma levels and defects per million opportunities, or DPMO. So first, you have to look at your data and is it continuous or variable data? A reminder from statistics that continuous data is a measurable characteristic that could take on any value, and a continuous variable should have a bell-shaped distribution following the normal bell curve. Using the capability indices, CP and CPK rely on a normal distribution and rely on having continuous data. So capability indices, CP and CPK, will describe what is considered the short-term capability, evaluation of your process. There are other similar capability indices that are such as CPM, Z-min, PP, and PPK, but we will not get into those in this case here. For all practical purposes, CP and CPK are considered the standard. So the capability indices compare your normal variability to your standards. And in order to do so, you have to understand what the standard deviation relies. The standard deviation will describe the spread of your observations. Following a normal bell-shaped curve, 68.26% of your observations will fall within plus or minus 1 standard deviation of that mean. Going further on out, 95.44% will fall plus or minus 2, and then 99.73% of the observations will fall within plus or minus 3 standard deviations of the mean. And the process width for CP and CPK is typically described as plus or minus 3 standard deviations. Plus or minus 3 standard deviations would give a 1.0 CPK, which we'll explain here in just a minute. That 1.0 CPK would mean that 99.73% of the time you would be within specifications. So CP and CPK are interrelated, but they're not exactly the same. CP is essentially your process potential. This compares the amount of variability to your engineering specification limits. So it looks and says how much, if the process were perfectly centered, how capable would the process be? This is done by taking your specification limits and subtracting the upper specification limit and the lower specification limit and dividing it by 6 standard deviations. And the reason it's 6 standard deviations, again, is because it's plus or minus 3 standard deviations on either side of the mean. This is important to understand the spread compared to the actual specification width. Again, it does not account for the centering of the product, and that's why it's called its process potential. A CP of greater than 1 would indicate that if the process were centered, 99.73% of the parts would be within specification. A large CP indicates the specification limits are large relative to the process variability, and so a larger is better is the measure of CP. Now, accounting for centering is where CPK comes into play. Since CP only compares the process variation to the specification spread, how would we describe the centering? Since CP only has the upper and lower specifications divided by 6 standard deviations, CPK uses 2 factors called the CP upper and the CP lower. So the CP upper is the capability index of the process to the upper specification limit, which is the upper spec limit minus the average divided by 3 standard deviations. CP lower is the same thing, only reciprocal on the other side of the bell-shaped curve, and that's your average minus your lower spec limit divided by 3 standard deviations. From there, CPK will look and compare whichever of those 2 values between your upper and lower CPU and CPL, whichever is smaller, will be your CPK value. It's important to note that if your process were perfectly centered, the CPU and CPL would both be identical, and in that case, your CPK would be identical to your CP. In other words, your CPK can never be better than your CP value. If you have a high CP value and a low CPK value, that tells you that your process is very capable if it were centered, and the result should be just to recenter the process. If you had a low CP value, you will never get the CPK higher than that, and you should look to reduce variability to improve your process. Since CPK compares the actual process mean and variability to the nearest specification limit, you can look at as the minimum of the upper spec limit minus the X bar over 3 standard deviations, or the X bar minus the lower spec limit over 3 standard deviations. Again, X bar being your process average. This will measure both spread and centering of the specification. A CPK greater than 1 will indicate that 99.73% of products will be within spec. And just like with CP, larger is better. First-time yield is defined as the percentage of units that pass through an operation the first time without any defects. This is a different take than CP and CPK and serves a slightly different need, whereas typically this will look at an overall process where CP and CPK may look at just one specific element of a process. This first-time yield is viewed from the overall customer perspective and shows the percentage of defect-free units. This gives the true voice of the customer. However, the downside to this is that it may suggest a process is performing better than it actually is, because defects could be addressed and fixed before it gets out to the final customer. Rolled throughput yield is defined as the percentage of end products that were defect-free throughout the entire process. This is a much tougher standard, and rolled throughput yield is usually going to be a lower value than your first-time yield. This will include all defects produced, even if it is corrected prior to reaching the customer. This represents the viewpoint of the process and internal stakeholders. Rolled throughput yield is much more valuable in looking at process improvement because it looks at all the defects throughout the process, and from a Six Sigma perspective, that is the valuable measure. Let's take, for example, this following scenario. Suppose you had 1,500 units that had 3 stages. Each stage, the first stage had 30 internal defects, but 22 of them were caught and reworked. The second stage had 15 internal defects, where 11 of them were caught and reworked. And then the third stage had 45 internal defects that had 34 of which were caught and reworked. Ultimately, with the catching and reworking of the defects internally, only 23 defectives got out the door, and you had 1,477 good product. This to show the difference between that first-time yield and the rolled throughput yield. The first-time yield would be taking the number of good units and then dividing it by the total. So 1,477 divided by 1,500, 98.5% yield. The rolled throughput yield, on the other hand, would be to multiply the percentage of good units at each step of the process. So to take that 30 defects out of the 1,500 gives you 98%. Multiply that again times 99% times 97%, giving the ultimate 94.1%. So, in summary, process capability allows you to understand the quality of a product or process, either the overall end-to-end or at a specific element or component within the process. It allows you to maintain standards for process management. So how do you manage on a daily basis, and where do you draw the line for I need to go and stop production or address issues as they occur? And then it establishes a baseline for continuous improvement. Regardless of which of those measures you evaluated, any one of those would be a good baseline for where you are today, and used a good follow-up measure to evaluate what you've done in the future if you've done continuous improvement efforts. Common process capability measures for continuous data are capability indices. However, for attribute data, first-time yield and rolled throughput yield are commonly leveraged measures.